Hi, welcome to one and all. Next, we will discuss about the conductor of a character. The conductor of a character chi can be defined like this: that chi be a digital character mode k. Then the smallest induced modulo d for chi is called the conductor of chi. So, if chi, the digital character chi has a induced modulo, then the smallest of that induced modulus will be the conductor of chi. So let us have a theorem immediate to this, that every Dirichlet character chi mod k can be expressed as the product chi of n is equal to psi of n chi 1 of n for all n, where chi 1 is the principal character mod k and psi is a primitive character modulo the conductor of chi. This is what we have to prove. That is, we have to prove that for every Dirichlet character chi mod k, we can express this as chi n equal to psi n times chi 1 of n for all n, where chi 1 is principal character mod k and psi is a primitive character modulo the conductor. Modulo conductor means the conductor, the smallest induced modulo conductor of chi. So the first part of the theorem is we have already proved, that is in the previous theorem we have proved that let us assume that D be the conductor of chi. Then D is the smallest induced modulo for chi by the definition of the conductor. Then by using the previous theorem we have proved that in the previous theorem we have proved that if D is an induced modulo, then there is a character psi modulo D such that chi of n is equal to psi of n chi 1 of n for all n, where chi 1 is a principal character modulo k. Here we have only proved that psi is a character modulo D, but we have not proved that this is a primitive character. So we have to prove that part. So by using this theorem we can say that we can represent, we can express this chi of n as psi of n times chi 1 of n for all n, where chi 1 is a principal character and psi is a character modulo. That we have already proved. Now further, if we prove that this D is primitive, then our proof is over. So now we have to prove that this D is primitive. That is, now we shall prove that psi is primitive mode D. We assume that psi is the method of proving is that we assume that this psi is not primitive, and then we end up with a contradiction. So that is the method. We assume that psi is not primitive mode D and arrive at a contradiction. If psi is not primitive mode D, then what is the meaning psi is primitive? Primitive means there is no induced modulo for less than D. So if psi is not primitive modulo D, then there is a divisor q of D where q is less than D, which is an induced modulo for psi. Now we shall prove that this q which divides k is also an induced modulus for chi. That is, we have assumed that D is the smallest induced modulo for chi. So we are going to contradict that this is not, D is not the smallest induced modulo if psi is not primitive. So that is our plan. So we assume that psi is not primitive mode D. There is a divisor D of q of D which is induced modulo for psi. So we shall prove that q which divides k is also an induced modulo for chi, contradicting the fact that D is the smallest induced modulo for chi. So for proving that, we have already seen in the proof of the previous theorem that n is congruent to, we are choosing n congruent to 1 mod q, GCD of nk is equal to 1. Then clearly we can see that chi of n is nothing but 1, and chi 1 of n is already 1, GCD of nk is 1, so this principal character is 1. So psi n of n, chi n of n will become psi n of n. So because q is an induced modulo for psi, so that is because we have assumed that q is an induced modulo. Hence q is also an induced modulo for chi, and that is a contradiction because we have assumed that the D is the smallest induced modulo for chi. So if q is an induced modulo for chi, then Q should be the smallest induced modulo for chi. So that is not possible. This contradiction arises because we assume that psi is not primitive. So our assumption was wrong. Psi is primitive, hence the theorem. Hope you have understood the theorem. Now we can have the next go to the next section, primitive characters and separable Gauss sums. Now here we have only one theorem based on this. The theorem is, let chi be a character mod k, then chi is primitive mod k if and only if the Gauss sum g of n chi is equal to sigma m mod k chi m e raised to 2 pi I mn by k is separable for every n. That is, we have to prove that if chi is primitive mod k, then g of n chi, the Gauss sum g of n chi is separable for every n. This is what we have to prove. But we have already seen that if chi is primitive, then g of n chi is separable for every n. This part we have already proved in the 8.15 b part. I will show the theorem. We have already shown that if chi is a primitive Dirichlet character mod k, then g of n chi is separable for every n. This we have already proved. This is by using the fact that g of n chi is equal to 0 for every n with the nk, gcd of nk is greater than 1. This is the fact which we have used. Using this, we have proved that g of n chi is separable for every n. So here this part we have already proved, so you have to prove it there here also. Then the remaining part. So if chi is primitive, then g of n chi is separable. So now we have to prove the converse part. That is, if g of n chi is separable, then we have to prove that chi is primitive. This is what we have to prove. So now that is, we have to prove that if g of n chi is separable, then chi is primitive. Now in the earlier theorem 8.9 and 8.10, we have seen that we have to prove that if chi is not primitive mod k, then for some r satisfying rk greater than 1, we have g of r chi is not equal to 0. Why? Because in this theorem, theorem 8.10, we have already proved that if this is separable, g of n chi is separable, then g of n chi equal to 0 when gcd of n chi is greater than 1. So this is what we have proved earlier. So if we need only prove that if chi is primitive, we need only prove that this chi is not if chi is not primitive, that is the contrapositive argument. If chi is not primitive, then g of n chi is not equal to 0. This is what we have to prove. So we prove that, suffices to prove that if chi is not primitive mod k, then for some r satisfying r gcd of r k greater than 1, we have to prove that g of r chi is not equal to 0. For this, suppose that chi is not primitive mod k. This implies k is greater than 1. Then chi has a conductor d less than k. Chi is primitive, then chi has a conductor d less than k. Let r is equal to k by d. Now then for gcd of rk greater than 1, and we shall prove that g of r chi is not equal to 0 for that r. So by previous theorem that we have proved that there is by previous theorem that there exists a primitive character psi mod t such that chi of n is psi of n times chi 1 of n for all n. This is what we have proved in the previous theorem. So in this theorem, where chi is here chi is primitive. So this is what we have proved. Now let us see this. Therefore g of r chi, by definition, g of r chi is sigma m mod k chi m e raised to 2 pi I rm by k, and this is equal to chi m. We have already seen that chi of n is psi of n times chi 1 of n, so we replace this by psi of m chi 1 of m e raised to 2 pi I rm by k. Now if we take this gcd of mk is 1, then our this will be reduced to chi 1 of m will be 1. So we have sigma m mod k gcd of mk equal to 1 psi m e raised to 2 pi I rm by k. Now here we have already taken r is equal to k by d. So this, when we replace r is equal to k by d, we will get this as psi m times e raised to 2 pi I m by d. Now here this is a reduced residue system modulo k, and if we decompose this, if we have a divisor d for k, d less than k, d less than k, that is d is greater than 0, it's a divisor of k, then we have then this residue system, reduced residue system, can be decomposed as the union of some phi k by phi d disjoint sets, each of which is a reduced residue system mod k. So by using this result, here we can replace this by summation m mod k, m mod d, instead of md equal to 1, psi m e raised to 2 pi I m by t. And for this sum we have some product also, this phi k by phi d will be there. So this can be decomposed as phi k by phi d times the sum, this sum, that will be same as this. That is by using this theorem, that is theorem. The result is given here. Now clearly, now we have seen what is this. This is nothing but, here by definition this is nothing but putting, instead of n we have 1, so this is for psi m. By definition of Gauss sum, this is g of r chi is nothing but for phi of k by phi of d, g of 1 psi. But we know that the absolute value of g of 1 psi, absolute value of this is square, is d by the previous theorem. So this means that this is a complex number, and it is its absolute value of this complex number is d. That means this is not, this cannot be 0. So this cannot be 0, that means, and this also cannot be 0. So this is not 0, this is not 0. So clearly this g of r chi is not equal to 0. Hence we have proved that if chi is not primitive, g of r chi is not equal to 0. But here chi should be primitive. So g of r chi is equal to 0. So chi should be equal to 0. Sorry, g of r chi is not equal to 0. So chi is not primitive is not correct. So we have to say that chi is primitive. Hence we have proved the result. I hope you have understood the theorem properly. Thank you for your patient listening. If you have any doubts or comments, please message me. Thank you.